Atomic spectroscopy. Now, when we talk about atomic spectroscopy, what we're looking at is either going to be absorption or emission. Absorption spectroscopy is going to be looking at the atom in the ground state. How much radiation is that ground state atom absorbing? If we're looking at emission, we're looking at how much of that excited atom is emitting radiation. So we have to excite it and then we measure what comes off. Versus in the ground state with absorption, we are radiating it with some wavelength of radiation, some energy source here. We're seeing how much is absorbed and then we will measure the difference. Now, regardless of which study we're doing, we have to get that sample into what's called an atomizer. The atomizer is the primary difference between flame, graphite furnace, and plasma spectroscopy. So the atomizer, and we'll spend a little time there, but not quite yet. So we get our sample and we get it atomized, okay? And regardless of whether it's absorption or emission, we're going to have some sort of a focusing lens, a wavelength selector. Then we're going to go to a detector. We need to amplify whatever the detector sees because it's probably going to be very, very small before we get to the signal processor. Once we get to the signal processor, then it's spitting out something that we can use. Now, when we're talking about absorption, we have to start with some incidence radiation. When we're talking about like a flame atomic absorption or graphite furnace or even ICP, we use this kind of a hollow cathode tube. This is the lamp that produces the wavelength of light of the element that we're looking at. Now, this is called a hollow cathode lamp, and sometimes we name things very, very well. You see, this is a lamp. It produces a light. It has a cathode, and every element we're looking at will have a different light because the cathode is made of the element of interest. So hollow because it's only really contains gas in there and it's kept as pure as possible. So hollow. It has a cathode of the element we're looking at and it's a lamp. Sometimes we name things just right. So each element we're looking at is going to have its own lamp. And that's one reason why absorption spectroscopy can end up being cumbersome for analysts. Now here is an example of a flame atomic absorption spectrometer. It's a benchtop machine. It might be 2 or 3 feet tall. It might be 2 feet deep. And it might be 3 or 4 feet long, but you see these lamps over here on the right. There are 4 of them. So this one can measure 4 different wavelengths. Each element we're looking at is going to have its own lamp. Now, a couple of things I want to point out with this particular machine is I want to show you this flame. See this flame right here? That's a really nice flame. Now, it may be tweaked for picture purposes, but when you're working with one of these, you really want to see that blue flame. What you don't want to see is necessarily something like, well, the flame is cut off here, but you see how it's kind of glowing orange up here? That shows you that the flame might need tweaked. Or you're analyzing sodium. Now, this picture in particular, hopefully you can see it, but there are these little tubes down here. And these little tubes, these are your sample inlet tubes. And they always, or as much as possible, they need to be in liquid. So what we're analyzing with a flame AA or a flame EA is going to be AE, not EA, but we're going to be looking at things that have been solubilized. Usually these are water containing, they're aqueous samples. So when you're not analyzing a sample, your little tube here needs to be in deionized water. Now, because we are primarily reading metals with these machines, you need to make sure that you are using deionized water and not just distilled water. So these were both examples of the flame AA. And you see it's called flame AA because there's a flame here. Now this flame is oftentimes produced by acetylene and oxygen, acetylene being the fuel and oxygen being the oxidant. And you can tweak the fuel and the oxygen in order to have either a lean or a rich flame. So a lean flame is going to have more oxidant or oxygen in this case than fuel, and it usually is going to run hotter than what's called a rich flame. So a rich flame is going to have more fuel than oxidant, and they tend to run a little bit cooler. It's a really good party trick, and I'm not going to encourage you to burn yourself, but it's a really good party trick to actually take your hand and pass it through this flame. It tends to be very exciting for undergrads to see such a thing. But this flame is usually about 2,500 Kelvin. Now, you do need it pretty warm because really you need to atomize your sample. You need to actually create some atoms. Well, you're not creating atoms, but you're separating the atoms from the solvent in an atomizer. Now, with the atomic absorption, we're talking about the absorption here. We do have to use these lamps, and it can be very specific, looking for your particular wavelength, or you can have a machine that has like these 4 different lamps. And honestly, I haven't seen one with 4 lamps, but it's been a while since I've run an AA. Mine had 2. So you can be specific with what it is you're looking for with absorption, but it can also be relatively cumbersome. Now, a flame AA is going to have less sensitivity than some of your other instruments or atomization techniques. And part of the reason for that is the background interference created by the flame itself. So remember, flames give off energy, and we can see that energy as light. And because what we're measuring is light, you have to take background readings and you have to subtract them from your analyte readings. If your analyte isn't well concentrated, it's going to be difficult even for some of our more high-powered instruments to subtract that background out as signal to noise. So again, absorption is a ground state phenomena. With absorption, we're measuring how many of those ground state atoms were absorbing that light. Now, the emission is actually very similar. You make a couple of changes with the instrument. So you either don't have these lamps or you basically turn them off. And then you switch your detector a little bit depending on your instrument. You probably have a little computer console. And you just make a couple of tweaks. In fact, you probably just click the emission button at this point. But then what you do is you read this color. Now, if you've ever seen fireworks, then you've seen the different colors that different metals can make. Now, most general chemistry students will do the experiment where you take a solubilized metal, let's say copper, and you burn it in a flame and you watch the flame turn green. So our different metals do produce different colors when they're heated like that. And what we're measuring with emission then is the radiation produced after the excited atom starts to relax. So absorption is a ground state phenomena, but emission is an excited state phenomena. Now, there are several things that can be adjusted with both the atomic absorption as well as the atomic emission for the flame kind of atomization machine. You can adjust the oxidant and the fuel in order to get a more lean or a more rich flame. And that, in turn, changes the temperature of atomization. So that temperature of atomization can affect how many excited atoms you have versus ground state atoms. For absorption, you can also adjust the intensity of the light that is produced. So flame is one atomization technique. Another atomization technique we have is called graphite furnace. And what we're doing with a graphite furnace, it's the same instrument, it's just a different atomization technique. And there's this wee little graphite tube, oftentimes no bigger than a drinking straw, like in width, but in length, you're looking at maybe 2 inches, maybe 3. It's not a very large piece of equipment. And they are consumable because you are heating these. And unless you are sparging very, very well with an inert gas, you're going to get some oxidation of that graphite tube, and they become sooty, and then they're fouled, and you get really poor readings with them. So you have this jacket of air around it in order to prevent that oxidation. Now, one of the benefits with the graphite furnace is not only can you use much smaller sample sizes, so you're using anywhere from 1 to 100 microliters of liquid. You can also sample in some solids. It doesn't have to be a liquid with a graphite furnace. Couple of caveats with the graphite furnace, though, is it's oftentimes a manual sample injection. So you are physically putting a wee little pipette in this little hole and putting your sample in. So reproducibility can be a problem with a graphite furnace. Now that can be overcome if you have an auto sampler, of course, but depending on whose budget you're looking at, that could be out of the realm of possibility. And then you have to deal with the sample fluctuations, if you will. Now, graphite furnace is just an atomization technique, just like the flame is an atomization technique. They're actually used in the same instrument. The output for a graphite furnace is going to be plotted over time. So we have absorbance on the y-axis and we have time on the x-axis. So what you get first here, this bit here, you're drying your sample, especially if it's a liquid to begin with. And then the first part of your slope here, you're charring your sample. And after the char, then you get to atomization and the peak of interest. So with graphite furnace, it takes reading it just a little bit differently. And that is going to be compared to something like this, which is a flame AA. And this is an integrated absorbance. So it's been cleaned up a bit, but this is a flame AA output. This is a spectrum. And notice the wavelength differences here in nanometers. We have 228.65, we have 228.8. So you see, we can get some really good resolution. See how we come from the baseline clearly up to a peak and then back down to the baseline? That's the resolution we're looking for whenever we're scanning with one of these instruments. You're looking for baseline, clear up, peak, and then come back down. And that's what we refer to when we're talking about the line width or the bandwidth that we're looking at. We're looking for that clear resolution in the peaks. Now, when you have an AA, or atomic absorption spectrometer, here's a flame diagram here, and it's basically the same thing. You have your lens, you have your photomultiplier. And the part I liked about this one, and not only did it show the HCl, the hollow cathode lamp, but also it showed that little tube in your sample solution. And typically when you have one of these and you're setting it up like in a laboratory, what you want to do is you want to have everything made, lined up and labeled so that you can dip the tube in, you press the read button, and there's a button and it would literally say read. And you have already set it to take how many replicate readings and such. And doing my work, I would oftentimes set it to take 50 replicate readings because I really wanted to make sure that I was really getting those degrees of freedom. And it goes quickly. You stick the tube in, you press read, and it does its thing, and it goes chunk, 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 chunk. And then you put it in the next solution, you hit read, and you put it in the next solution. And you never have that tube out into air longer than you need to, which is why you always have deionized water around. Now, most of the time, or I should say sometimes, you can have what's called a double beamed instrument. We introduced double beam instruments in the last week of this particular module. And a single beam instrument, so would be something that's just going to read what you're putting into it. But a double beam instrument is going to have a reference beam as well as your sample beam. So if it's absorption, then your reference beam is basically going to be reading what comes through the flame without a sample. And you have this beam chopper here, and it cycles back and forth so that then the display and the detector can read what those differences are and can automatically take that reference away. So all of this is to try to make the sampling and the analysis as easy as possible for the analyst. So we have flame AAS, we have flame AES, so emission. We have graphite furnace AAS. We have graphite furnace AES, so emission. We also have what is called inductively coupled plasma, and that's the most sensitive way to analyze a sample, at least like trace metals and such. So inductively coupled plasma, it's called ICP. So ICP, inductively coupled plasma, it looks a bit like this. It's really kind of cool. But ICP is a very, very expensive technique. It's also very sensitive. ICP not only is the instrument expensive to purchase, but it uses a lot of gas. So the consumables are very expensive as well. Now, ICP-MS, or inductively coupled plasma, that would be our atomization source, mass spectrometry, is probably our most sensitive technique that we have to use. So ICP being the atomization, mass spectrometry, you probably had some introduction to in organic chemistry. And what happens with mass spectrometry is your sample is bombarded with energy, and it creates ions. And the mass spec will separate those ions out by mass. So if we couple these techniques together, we can not only be qualitative and say what we have, we can be quantitative and find out how much. So ICP is a fantastic analytical method for things like trace water analysis, for heavy metals and such. ICP-MS has also been used in archaeological studies because we can differentiate between isotopes. So this is a great technique. Not every school has an ICP. So if you don't have one in your lab, it's okay. But the plasma gets very, very hot. You see these temperatures, 10,000 K, 8,000 K, etc. And this is what's called the torch, the ICP torch. It's usually a high-grade quartz, and I had a tendency to melt mine, so I got to know the glass blowers very, very well at Virginia Tech. So we have these different techniques, and I just said that the ICP-MS is probably going to be the most sensitive. So this has the highest sensitivity. It's also the most expensive. Sensitivity, I can't spell it. It's also the most expensive. Now, the flame, both absorption and emission, that's going to be the lower cost. So if you're going to do something quick and dirty, you always use a flame first. Furnace, it uses the same machine, but those graphite tubes can get expensive with their consumables. So although the machine cost is usually taken care of once you have an atomic spectrometer, having the graphite furnace module to insert instead of the flame can be another expense that not every school is willing to take on. But the flame emission spectroscopy, that's the most common, and that's what I imagine you'll be using in the laboratory, is either the emission or the absorption for the flame, purely because more schools have it available. Now, being ICP with mass spec, this is an emission. There are no lamps to worry about. There's very low background noise. There's low interference because it's emitting, and we know about the plasma flames very well. It's usually an argon or acetylene plasma. So I have just thrown out a whole lot of words. How do we use these things? Well, what does the temperature have to do with anything? I mean, I just said that ICP-MS is very expensive and it gets very, very hot. Well, big deal. Why do we care about what temperature it is? Well, the temperature of the atomization has to do with how much of your sample becomes excited and how much is in the ground state. And we have what's called the Boltzmann distribution. So we use a capital M with a superscripted star or asterisk, and we put that in ratio to a capital M, N, with a subscripted 0 or naught. So what this is known as the Boltzmann distribution. And what we're relating are the degenerate states of excited atoms to ground state atoms. And we relate that by multiplying it times the base E. Base E is the base of the natural log function raised to a negative delta E. So the energy found, remember the energy we found to be HC over lambda. Remember that? Well, we're going to use it over here. And that exponent, the delta E, is then divided by a lowercase k, capital T. Now, lowercase k is called the Boltzmann constant. The Boltzmann constant is 1.381 times 10 to the negative 23rd, and the units for that are joules per Kelvin. So that right there should tell you that the temperature needs to be in Kelvin. So the temperature does have to do with this stuff. It has to do with how many of our atoms are excited versus ground state. And therefore, we can tweak like our flame to be hotter or cooler to then change the ratio of ground state versus excited state so that we can tweak our emission or absorption sensitivities. So let's just say we have a ground state atom and it's going to absorb a light of wavelength 400 nanometers. And we're going to promote that atom into some sort of an excited state. So what's going to be the energy difference between these two states first? And if we declare that there is a degeneracy, can't spell it, of 2, that means the G star over G naught is going to be equal to 2. Then what is the fraction of excited state atoms at an equilibrium temperature of 2500 K? Well, this N bit here, this is our fraction of excited to ground state atoms. This is what's called our degeneracy. So let's start this calculation by finding our delta E. Well, delta E is going to be equal to H, which is 6.626, times 10 to the negative 34 joules seconds times C, which is the speed of light in a vacuum, 2.998, times 10 to the 8th meters per second. And all of that is going to be divided by the wavelength, but we have to convert that wavelength into meters. So 400 nanometers times 1 meter over 10 to the 9th nanometers. And I get a delta E, or an energy, to be 4.966 times 10 to the negative 19 joules. So now that's going to go into my Boltzmann distribution equations. So I'm going to switch my colors here. So I'm going to have my N star over N. That's what I'm looking for. Now the G star over G naught, that's called the degeneracy. And I'm told in my problem that that is equal to 2. That's nice and inconvenient. Then I need to multiply that by E raised to the power of, let's get rid of these. The calculated energy we just calculated, 4.966 times 10 to the negative 19 joules. I'm going to divide that by the product of the Boltzmann constant, 1.381 times 10 to the negative 23rd. And that's joules per Kelvin. Now I need to multiply that Boltzmann constant by the temperature. The temperature must be in Kelvin. Happens to be in Kelvin. That's convenient, 2500. When you punch all that into your calculator, the most common mistake I see is forgetting the negative sign. So make sure you have that negative sign. Now to get to E in my calculator, what I would hit would be 2 and then my multiplication button. Then I would hit second and LN, because my LN key has an E with a box over it. And that's the color of my second button. It might be your shift button. It might be a second button. I don't know what else the calculators would have. But if you aren't sure, then send me a picture of your calculator and I will help you find the keystrokes. So when I do this arithmetic, I get that my N star over N naught, which is the fraction of my excited state atoms to ground state atoms, is then 1.14 times 10 to the negative 6. Now this shows me that I have far more ground state atoms at 2500 K than I do excited state atoms. Now, most of the problem solving for this particular chapter is going to be related to our QA and QC chapter. So we will be looking at LODs and LOQs. We'll be working with standard curves. It's all stuff that you've seen before. We're just using atomic absorption data to work with it. So it's not difficult to do this problem solving. It's just going to take remembering how to work those problems. So for example, for this internal standard problem, this is one of those problems where we're looking at the absorbance of one of our elements over the concentration of that element is going to be equal to some factor that we need to calculate, and that's going to be multiplied by the absorbance of our other element divided by the concentration of that element. So we need to calculate this F based on our standards. So what I'm going to do is start filling in our values. We have 2 micrograms of manganese per milliliter in our standard. So I'm going to put that right here, 2.00 micrograms per milliliter. The ratio, so I really should solve. So the ratio of Fe to Mn is going to be 1.05. So if I solve for Fe over Mn, then I have AFe over Amn is equal to F times the concentration of Fe over 2.00. And then this is 1.05. So the concentration of the Fe given here is 2.5. So all I have to do, because these are both micrograms per milliliter, they cancel out. Now all I have to do is calculate F. So F is going to be 0.840. Now I can use that with my unknown, 0.840. So I'm going to fill this back in because I actually need to calculate that concentration. And I'm going to fill in the numbers that I know. The absorbance of the unknown mixture at the manganese wavelength is 0.128. That's this value here. The absorbance at the iron wavelength is 0.185. Now, I have one equation. I have 2 unknowns. I should be able to figure out one of these unknowns before I have to calculate. So let's go back up and finish reading. A mixture with a volume of 6 milliliters was prepared by mixing 5 milliliters of an unknown Fe, we don't know Fe, with 1 milliliter containing 13.5 micrograms of manganese per milliliter. So how many micrograms of manganese did we insert? Well, we put 13.5 micrograms of manganese in that unknown, and it has a total volume of 6 milliliters. So in order to keep my my concentration units micrograms per milliliter, I have to divide. So this concentration becomes 2.25 micrograms per milliliter. Now all I have to do is solve for my iron. And I get that the concentration of the iron is 3.96 micrograms per milliliter, but we aren't done. So that is the concentration of the iron in the mixture. That's in a total of 6 milliliters. I had 5 milliliters. So I need to multiply this by 6 milliliters and then divide it by 5 milliliters in order to get my original iron solution concentration of 4.7, and I think I'd round that, 4.76 micrograms per milliliter, and that is the concentration of the iron in the original unknown.